introduce Ethan. Ethan is a staff research scientist and co-founder of a research team at Google that takes a scientific approach to understanding machine learning. He received his PhD in theoretical physics from MIT in 2014 and was afterwards a postdoc at Stanford and Johns Hopkins working on theoretical physics, ML, and genomics. We're delighted to have him tell us today about neural scaling.
Thanks a lot. Yeah, thanks for inviting me to speak. And it seems like a really fun series, so I'll definitely sign up and try to attend in the future. Today, I'm going to talk about some work that's done in collaboration with Yasaman, Jared, Jehun, and Utkarsh, who are all part of the physics diaspora. And so, as I'm sure many of us here are aware, models have been getting bigger and bigger, using more compute, but also correspondingly improving in performance. And so the question that sort of motivated this work, and that I'm going to talk about today, is sort of a narrow slice through the question of how do big models work. And one of the dangers of making any, let me also say, so I'm not able to see people and see my slides at the same time. So like, rather than being polite in any way, please just like unmute and interrupt me at any point for any reason, and that's more than welcome. Great, so yeah, so and models are getting bigger and better, like within a week, gets out of date. So like, here's an example from the 8th, where just by scaling up vision transformers, a team from Google reached a new state of the art on ImageNet, and maybe even more exciting than that. So they're able to get 84.9% accuracy on ImageNet with only 10 examples per class. And so this is a paradigm where you do a lot of unsupervised, or you do a lot of pre-training before fine-tuning on ImageNet. Okay, and so when I show these plots, often there's some particular metric plotted, like we're looking at performance as you scale up in terms of loss or in terms of classification accuracy, but this also usually plays out in terms of performance on lots of interesting downstream tasks that we care about. So for example, here is a plot showing aggregate performance of GPT-3 models at different scales, evaluated over a whole range of text tasks. So for instance, summarization, question answering, entailment, these kind of things. And we see that the performance on these tasks seems to improve systematically with scale over many orders of magnitude. And if we could imagine extrapolating this for a few more orders of magnitude, these models would be broadly superhuman over a whole range of tasks. Now, in addition to this impressive performance, there's also evidence of simplicity as we make models larger. So the maybe simplest, most well-known version of this is that if we think about networks that are getting wide at a fixed depth, then in a limit of infinite width, they approach linear models. But people have also studied taking infinite depth or taking combined infinite depth, infinite width limits, and found analytic simplicity there as well. And then on the empirical side, there's also evidence of simplicity, in particular over many orders of magnitude in data set size and parameter count. We see something that looks, at least qualitatively, like power law scaling over many orders of magnitude. And so I'd say both of these, or all of these seem like it means that studying models at scale are sort of promising in terms of maybe being understandable, but also relevant for practice. But in terms of our current theoretical understanding and what we typically see in practice, there's a qualitative discrepancy. So typically, we get some theoretical expression. So for instance, this is an example taken from Random Kitchen Sinks paper by Rahimi and Recht, which is studying linear models, but you see similar expressions in wide network literature, which I'll discuss more later. But you have generalization bounds, which are typically data independent and typically give you some fixed scaling with dataset size D or parameter count P. And in contrast, and these are typically either half integer or integer type scaling laws. And in contrast, what we see in practice is something that looks like power law scaling, but with non-trivial data dependent exponents and typically taking on values in between 0 and 1. Right, so this talk is going to be a tour of 4 different scaling regimes, namely going to look at underparameterized models scaling with data set and model size, and overparameterized models scaling with data set and model size, and try to walk through these regimes and sort of understand what's underlying both the theoretical scaling bounds that we see and also the scaling results that we see empirically. We'll organize this into 2 qualitatively different types of behavior, which we've dubbed variance-limited scaling and resolution-limited scaling. And the variance-limited scaling is appropriate for underparameterized model scaling with dataset size, or overparameterized model scaling with model size. So right, so just to give an outline. So we've already completed the introduction, and I'm going to walk through these variance-limited scaling behavior, then talk about this resolution-limited scaling behavior. Then I'll describe a solvable model, a kernel model using random features that's able to realize all of these different scaling regimes, and then I'll conclude. Maybe before continuing, any questions?
Are you going to focus mostly on the large model size, or also are you going to talk also on the like small model, small data? Small data you mentioned, but like small model size.
So I will always talk. So everything that I'll say will be asymptotic, but not necessarily in model size. So I'll continue. So the 4 regions, if I think about the variance limited scaling, that can be small data, so fixed data set size, taking model large, or large data, fixing small model. Whenever I talk about the resolution limited scaling, that will also always be a double scaling limit, where let's say I'm talking about over-parameterized models, then I'll take the model size huge, but still consider the scaling as a function of data set large. So all the scaling behavior will be in the asymptotic limit, but in this variance limited case, the thing that's not scaling can be fixed and small, whereas in the others, everything is big.
Thanks.
Thanks. All right, so let's start with this variance limited behavior. And as I mentioned, this will be describing underparameterized models, data set size scaling, and overparameterized models, model size scaling. Okay, so the central structure underlying this variance limited scaling is that if I have a random variable which concentrates around its mean, then sufficiently smooth functions of that random variable will also concentrate. So for instance, if I consider some random variable A with some mean A bar, and with higher moments taking on some small value, let's say order epsilon, then if I think about the expectation of a smooth enough function of A, and I sort of naively exchange my my Taylor series and my expectation, I find that the function of A is also concentrates around the function of the mean of A, and in particular, the corrections to that are just controlled by the variance of this random variable. So in this example, it would just be order epsilon. And so the idea here is that for either large data set or large model, we have exactly the situation where the concentration is coming from the fact that this random variable is an average over many independent quantities. So for instance, if I think about the large data set size, then each data point is IID, and so means of functions of these data points just concentrate with central limit style scaling. And so we can be explicit about this. So if we, for instance, focus on over-parameterized model scaling with model size, so again, reminding you in the large width limit at fixed depth, these networks approach linear models, and in particular, the corrections to this linear behavior scale like 1 over the width. So here, just to make notation clear, the total number of parameters goes like the width squared, and so here I'll denote the width by n and parameters by p. Sorry. Sorry about that. Right. Okay. Sorry. So in this large width limit, one can systematically work out the expansion of the network function, target function f, as an expansion in 1 over width, and one finds some leading time-dependent behavior for the network output when trained under gradient descent or gradient flow, which is just the same as what one would have gotten in a linear model. But then corrections are controlled by this 1 over width. And so here's an example showing this where the blue is actual evolution of a 2-layer network. With the linear evolution subtracted, the black line then would be the just the linear model prediction, and the dashed line is what one gets by including 1 over width corrections. Gives a loss which approaches its infinite width behavior just like 1 over width. And that's also indeed what we see empirically. The infinite width loss can be better or worse than the finite width loss, but it approaches its infinite behavior with this fixed mean field data independent style scaling of 1 over width. In a similar vein, one can work out an expansion in dataset size for a fixed small model, and there are a few different ways to see this. So maybe the simplest is if we think about the loss function on a finite training set size. And if we think about this as a random variable over draws of our training set, then this variable concentrates around the true test loss, but with variance that scales like 1 over data set size. And so if our optimization procedure is a smooth enough function of this training loss, then the weight that we get out at the end and the test loss that we evaluate at the end will also differ by 1 over data set size. And just to get some intuition, if we think about, for instance, the initial gradient, this is just a mean over our here under gradient descent. This is just a mean over all of our all of our training data points, and so concentrates around the true gradient. And so indeed, if we look empirically for a variety of network architectures, losses and optimization choices, we see that in these regimes, either the small model, large data set size scaling, or the small data set, a large model size scaling, we get losses which approach their infinite behavior with exponents that seem relatively close to what's predicted by this variance-limited argument.
Can I ask a question?
Of course.
I guess I just did. So when you talk about a large model size limit, what is being held fixed? Like, I understand what's being held fixed in the large data set limit, but how sensitively does this depend on the details of how one takes a large model size limit?
Yeah, so I think like the most broad answer is that's a good question. I can give some examples where it does like where we know sufficient things to hold fixed that this behavior is derivable. So like if you hold the data set size fixed, the depth of the network fixed, take the width large, hold the number of training steps fixed, and hold the learning rate fixed below some critical value, then one can derive all of this behavior. Now, it's empirically, it seems like the answer is more general than that. So I mentioned that one has to keep the learning rate below some critical value to be able to have this property. Empirically, it seems like the scaling holds even if one takes the learning rate above that critical value. There's work on combined depth width limits that hint at a similar situation. I think so. Anytime I have a large model limit that that's well defined, where it goes to some limiting value at large model plus fluctuations with some controlled variance, then the difference in my loss will just be controlled by those fluctuations, unless something singular is happening. Just by this,
general law of large numbers kind of, or general central limit theorem kind of stuff.
Well, so the central limit maybe gives you that things should concentrate with these fluctuations, but I'm saying, let's say for whatever reason, we know that things concentrate for the model output, then I'm saying then the concentration for the loss just follows by like plugging in the model into the loss and Taylor expanding. Right. Now, of course, if you're, maybe the loss isn't amenable to Taylor expansion, something like that. But let's just say generically, if I knew that I had a well-defined large model limit for my model, then the well-defined large model limit for the loss is just controlled by this variance.
Okay, thanks.
Does that make sense?
Yeah, no, it does. Thank you.
Just also another clarification thing. When you say you're varying over optimizers, you're essentially varying learning rate, or you're adding also things like momentum and stuff? Or?
So what we have in the paper is just full batch and SGD.
Okay.
But no momentum. Well, yeah.
Okay, yeah. Just wanted to know which kind of optimizers it's coming from.
Yeah. So in the resolution limited regime that I'll talk about, we just consider like sort of normal momentum with cosine decay optimizers. So rather than non-standard, rather than toy optimizers. Cool. Okay. So that's the picture for this variance limited scaling. And now I want to talk about this other regime, this resolution limited regime. So right. So here, for instance, we're taking, in the over-parameterized case, we'll take the models bigger than anything else that we're discussing, and then ask about scaling with data set size, or in the underparameterized case, take the data set size bigger than anything else, and discuss the scaling with model size. Right. So so what is the mental picture here? So I'll first talk about the data set size scaling for overparameterized models. And so so here, yeah, I want to describe a picture. I'm not going to derive that this is literally what neural networks are doing. I just want to say that if neural networks are doing something like this, then we can understand the scaling in this case. So let's imagine that that we have some data manifold that's d-dimensional, and that what we're trying to learn is some target function, fancy f, over that data manifold, which is some smooth enough function over this data manifold. And our training and test data are just drawn randomly IID from this data manifold. And let's imagine that what a network does is on some new test point that it hasn't seen before, say this maroon, the maroon point in this picture is supposed to represent the new test point, and the blue points are supposed to represent training points. Let's say that the model just predicts the value that it has at the closest training point. And again, here, since we're imagining the model is bigger than anything else in the game, we imagine it can say perfectly fit all of the training points, all of these blue points that we have. Okay, so we have some prediction which is made at some close point, which is just the closest training point. And so we can ask, if this is what networks are doing or something like this, how do we expect the loss to scale in that case? And so again, we can just take our loss on our new test point, and we can just look at what had happened if we just expand around the close training point. What we get just expanding this is that the leading behavior of the loss is just given by the difference in the distance between the test point and the closest training point. And so then asking how this loss scales is asking, if I sample d training points and then a random test point, what do I expect the scaling for this nearest neighbor distance to be? And so then it just becomes, how do nearest neighbor distances scale on a manifold of dimension d? And they scale like the number of points to the -2 over dimension of the manifold. So, you know, as I add more points, the distance becomes smaller. As my manifold is higher dimensional, then that scaling happens more slowly. And so that, you know, that 2 over d is the cursive dimensionality factor for the d-dimensional manifold. And if you want to derive this, one can just think about, for instance, scaling if I imagine points on a regular lattice, but it holds more generally. Right. So just to emphasize, this scaling behavior can take interesting values. In particular, it can take non-integer, half-integer values. In this case, between 0 and 2. And so it's richer and data dependent when compared to the variance-limited exponents that we discussed before.
And question, I mean, this definition of, this is very close to the definition of like Hausdorff dimension. So at least naively, it's not even obvious to me that little d needs to be an integer, right?
Fair enough. Yeah. Yeah. So so one way to actually define, I mean, so yeah, Hausdorff dimension is one thing you could do. There's various other ways. One way to define it that is like just one step removed from how we're even using it is you can use distribution of nearest neighbor distances to actually try to define the dimension of the manifold.
Right.
But then of course that's just
right. That's pretty close to the Hausdorff dimension
Yeah,
anyway.
yeah,
I don't know if it's exactly the same. Yeah. Great.
Yeah. I mean, there's also, yeah, I mean, there's whole discussion, philosophy to say about what one actually means by dimension here. There's implicitly a scale that we're talking about too, right? Like, the data points are their own islands. It's only really a manifold, like once you imagine coarse graining at some scale. And so as you probe D, it's possible that, you'll actually see, as you change capital D and are probing the manifold at shorter and shorter distances, of course, what you're seeing is the dimension can potentially change, for instance.
Right.
But
or I imagine that what you mean by little d is some large D limit of whatever that process would be.
Mm-hmm.
But I don't need to distract you. Thank you.
Yeah. No, great. Right. Okay. So how do we discuss this in the other regime in this underparameterized picture scaling with model size? So before we had the data was drawn from this smooth d-dimensional manifold, but now we're in this data bigger than everything else in the game limit. So we can just say that like data makes up this smooth d-dimensional manifold. And what we're trying to do with our model that now has finite capacity is we're trying to come up with a coarse grain approximation to this smooth manifold. As we add more and more capacity to our model, we are able to approximate this smooth manifold with better and better resolution. And this again gives the same qualitative scaling behavior. Like, for instance, if we imagine that our model can represent an arbitrary piecewise linear function, where the kinks in this linear function, the vertices, sit on the true manifold, but then it's restricted to be piecewise linear with number of vertices given by the number of parameters, then we get a scaling which again looks like now the number of parameters, but to an integer over this intrinsic dimension of this data manifold. And here I put number instead of 2 because, for instance, if you meet not just the value but also the first derivative, at each point, then you can do a little bit better. You can get a scaling which is 4 over D. But generically, if all you're doing is approximating the value at each point, you again would get 2 over D. Right. So then comparing this to what we see in practice. So here, here's now the fully unmasked version of this plot. So in the variance-limited case, we saw these exponents which didn't care about the underlying data set that we were using. And in this in the resolution-limited regime, now we see that the exponent takes on non-trivial values and is different for different data sets. Okay. Great. So So now I want to talk about an explicit case where we can realize all of this behavior very concretely.
Can I ask maybe a dumb question? If I go back to the plots that you showed on the previous slide, where you had these resolution limited things, all of the scaling exponents, they're all kind of order 1-ish, which means that basically this is a statement about the little d dimension of that manifold, from which things are being drawn. Why is that low dimensional? Right, because alpha's not close to, right? I guess alpha being order 1 means that this is a low dimensional manifold.
Yeah.
What is that teaching us anything? Why is it low dimensional?
Yeah. So
right. What do we learn? So are you learning something deep about the structure of the data sets that are being characterized here? Yeah, that sounds like it's teaching us something. So what is it teaching us?
Yeah, so I mean, again, I can give you some heuristic picture, and then we can talk about various ways to be precise about it. But you could compare this with the numbers that I showed you, for instance, for like text modeling tasks, where like so these numbers are
Those
pretty
like
big.
0.1 or something like that.
Yeah, so those were like 0.1, or in some cases you can get even smaller. So it seems to be the case that like the complexity of the task and this exponent are, you know, like are very related. So even in the text case, if you do something like translation rather than just to give some background, maybe you already know, sorry if I'm repeating, but like the text model task that I showed you was like we're doing next word prediction. And so this is like in some ways a very unstructured task. Like there's the complexity of that next token prediction is quite high. And if you compare that to like similar underlying data, but a different task, which is say like translation. So there, like that's quite, I'd say a quite restricted problem, and that you have just like, you know, a limited choice of options for what you're supposed to output, like translating a word compared to like what's the possible next word I could say in a sentence. And so translation, you see exponents which look more like this image classification exponents. And next word prediction, you see exponents which look like a much higher intrinsic dimensionality. Similarly, if you look at these numbers here, they're sort of getting higher dimensional in a sense which like sort of matches our intuition about the complexity of these tasks. So, here like CFAR 100 is harder than CFAR 10. Mm-hmm. If you look at these numbers for ImageNet, you also see that ImageNet looks harder than CFAR. All of the tasks shown here are relatively simple, 10-way or 100-way classification tasks. I'll have something to say about the number of classes in a minute, which makes me, it's not true that the complexity is just the same thing as the number of tasks, the number of classes that you have in your data. But the number of classes is a proxy for sort of how complex multimodal your underlying data distribution is. And so I think the real answer is that, yeah, so these are like sort of relatively simple few mode image classification tasks is why they're similar. And if you have a much broader distribution, you'll see a higher dimension.
Great, thank you. And maybe while we're staring at these plots, one of the things that I noticed in the resolution limited case in the lower left-hand corner is that there actually looks like there's a kink. Like it looks like one straight line and then another straight line.
Right. So
going on?
Yeah. So if so the setup, if you remember for that for these regions is like I need to take so let's see. So this is taking width large. So I need to have data set larger, like much larger than anything else in the game to be in this asymptotic scaling limit. And unfortunately, these are like real finite sized data sets.
They're too small. So that's where you're just not in the right limit. Okay, great. Yeah. Oh, in fact, so in principle, I guess you could go over to the variance limited if you really scaled things up. Yeah.
Yep.
Okay. Thank you.
And maybe just like if this is in people's heads at all, if you think about the double descent picture, like where you have like, let's see if I can draw this in Zoom, you have some descent and then you have a bump and then you have another descent. The resolution limited is that sort of left, it's like if you scaled up everything there, so sort of moved the peak out to the right. The variance limited scaling is telling you about that first fall to the peak, and then that's the resolution limited scaling is telling you about that first fall to the peak, and then the variance limited scaling is the approach of your, after you pass the double descent bump, that's your approach to your large, model size floor.
Great, thank you.
Cool. Okay, so right. So how do we get our hands around what's actually going on? Well, here's a model where we can see all of this behavior. So the setup is going to be a linear random feature model, a teacher student model where we have some teacher capital F of X, it's built out of some collection of features, capital Fm of x, weighted with some weights w. And we have some student with p parameters, little f of x, with weights theta, and features f mu of x, which are just some subset of these teacher features, and these weights theta we will learn. And so if we imagine training our student, say under MSE loss, and training for infinite time to the global minimum, we just get a loss which looks as follows. It's the difference between these two kernel expressions, where this kernel is the data. In this case, NTK is the same as just the RKHS kernel. So this is just a kernel built out of the teacher features, and the Ks with various decorations. Here, let me close the window. I think there's some noise coming in. Sorry, there's street cleaning going on outside. Can people hear me okay?
Yeah. Yes.
Sorry about that. Yeah, so the kernel is built out of these features, and then the kernel with various like bar decorations indicates that we're evaluating this kernel on training set points. So K bar is the kernel evaluated with both indices on the training set, and K vector indicates one index on the training set and one on an arbitrary point. And so if K bar was the same as K, then this loss would just be 0. And indeed, if we scaled the data set size, to infinity, that's what we would find. But the non-trivial finite value of this loss comes from the fact that the kernel on the training set is different than the kernel evaluated over all of the data. Okay, so this is what our loss looks like, but we'd actually like to understand its scaling properties. And so for that, we have to understand what's a reasonable ansatz for this kernel. And maybe in choosing this ansatz, I want to give some background perspective on what these kernels can look like. And it's sort of reminiscent of universal versus integrable systems that we see in physics all the time. So on the left, what I've plotted is the spectrum of a one hidden layer. So features built out of a one hidden layer network, ReLU network, evaluated on data that's uniform on the sphere. And on the right, I've plotted similar features, so random ReLU networks, but now evaluated on MNIST. And here the colors indicate taking MNIST and pooling it at different scales. And so the point is, the features coming from these networks, they have some rotational invariance, and if we take our data also to be uniform on the sphere and have this rotational invariance, then we get a spectrum, which is highly degenerate. But if we look at what sort of realistic data spectra look like, they don't look like this. They look more like sort of single power law over large swaths, little degeneracy within the eigenvalues. And so, one in some of these integrable data distributions, you can solve exactly for the behavior of these models, but a key aspect to capture realistic scaling is to consider data that is sort of more universal and less integrable. So inspired by that, we'll consider kernels where the spectrum is described by a power law, and here parameterizing it just as 1 plus alpha k.
So naive question probably. I see that there's always one kind of outstay. So at the beginning, the spectrum seems like kind of very well spaced and a lot of hierarchies in there. Kind of if I look at it, there's some,
You think of these guys up top?
These guys, for instance, yeah. And then at the end, it becomes pretty much continuous. Is there some story to this?
That's so in the large width limit, which these you could debate whether these are or not. Then there is like one can solve for the structure of the spectrum, and there's a top, like the NTK, for instance, has a top eigenvector corresponding to like the all ones on all the data. So in that limit, you can understand why the spectrum has this one eigenvector which jumps to the top. I mean, here these are something like with 100, and so maybe it's like, yeah, you could imagine it's like a leftover remnant from that behavior.
Yeah, thanks.
I'm wondering if you could say how you computed that graph in practice in the previous slide.
This one?
Yes, this one.
Right. So this just comes from. So I just you have a matrix which is MNIST size by MNIST size, and then you just in fact you can do a little like you can look at, so this is an outer product of a feature size by MNIST size matrix, and then you just do the singular, like explicitly numeric singular value decomposition and plot it. So no theory so there, just empirics.
This is directly looking at the dot products of inputs, not the dot products of gradients, right?
Correct.
Okay, thanks.
By inputs, this is like feature, so this is a linear model with some number of features, and here it's the features evaluated on those inputs.
Okay, got it. Because I saw in the NTK literature, they sometimes compute the kernel by looking at gradients. So they do the dot products.
Yeah. So yes. So like so here are that's typically the gradient of the model output. And so if you have a linear model, then your model just looks like weights times some features.
Right.
And so the gradient of that model output is the same as just the features of that linear model. These are different when the model is not linear, but for the linear case, they're the same thing. Does that make sense?
Yep, makes sense.
Okay.
Cool. I have another question. So in that plot, I is iterations or steps?
I is the index of the eigenvalue. So this is just, I have this kernel, I'm plotting its spectrum, I'm plotting all its eigenvalues. I sort them from biggest to smallest, and I just plot it index versus value.
Okay, thank you.
No problem. Great. So so with this ansatz, one can actually solve for the behavior of this loss at large D. So one can use the replica trick to compute this explicitly, but to get just a sense for the scaling, there's actually some easier intuition to see what's going on, which is that if I think about large alpha K, then it's clear that the top part of the spectrum of K on the full data will match the top part of the spectrum of K evaluated on the training set. And so what this expression just gives me is this is a trace. So I get the sum of all the eigenvalues of K, but then I'm subtracting the top eigenvalues, the top D eigenvalues in K bar, and so this gives me something which looks like the sum of the tail of the spectrum up from D+1 up to infinity. And so this gives me a scaling which scales like dimension to the minus alpha K. And so one can also do a similar computation in this model for model size scaling. And so we see that if we put in, by hand some power law for the kernel spectrum, then we get a power law, corresponding power law for either the scaling of the loss with respect to data set size or the scaling of the model with respect to number of parameters. And so, this begs the question, okay, fine, like, but what, why did you put in this power law scaling for the kernel? And I mean, I gave some just empirical evidence that like in MNIST it looked pretty good, but one can say a little bit more, which is that actually there are classic bounds on the behavior of the spectrum of smooth kernels on manifolds of d dimensions, which is that if a kernel is, you can phrase this in various ways, but one such bound is if the kernel is in CT, then the spectra have to be bounded by something like this. So something like I to the 1 plus T over D, and so alpha K in this case would just be T over D. And this actually goes back to work by Weil, and the statement is that so this is always true, but generic non-integrable kernels not just satisfy this bound, but saturate this bound, and so have this kind of power law type scaling generically. And so that gives this picture where if you imagine a smooth generic kernel on a d-dimensional manifold, then that gives you something that looks like power law scaling for the kernel spectra, and then that in turn gives you power law scaling for the data set size and model size. And okay, one can go and measure this explicitly in these kernel models, and indeed you see the variance limited and resolution limited scaling in this setting. Okay, so just to conclude this thrust, there's 4 scaling regimes. This resolution limited scaling perhaps has this interesting geometric origin. I should emphasize also that this resolution limited regime is typically more interesting in practice, just because you're scaling the parameter that's actually bottlenecking your performance. So just for instance, if I think about over-parameterized models with a small data set size, as I increase the model size, the model is not really the thing that's limiting my performance there. So the scaling with model size, is good to know, but it's not the thing that I'd scale if I wanted to do better on the task at hand. So rather, for over-parameterized models, it's typically the data set size that's bottlenecking you. So understanding the scaling there with data set size is telling you more about like the practical improvement of models where you're scaling the thing that you would scale to do better. And then kernels are able to realize a solvable version of these regimes. So I've been somewhat fast and loose with this data manifold. I just called it little d. There's I sort of made up a fairy tale about how neural networks in reality might be performing doing this nearest neighbor type interpolation or something like that. But there's a question of like, well, what actually is the data manifold in practice, and how do you see it? And then I've these manifolds typically drew and sort of think in my head in terms of the input data, but of course, like for the plots I'm showing, we're doing some classification tasks role to the targets play, and we can look at this a little bit. So here's some plots looking at on the left, take CFAR 100, and we always use the same data, but we change the labels. So CFAR 100 has 100 classes. But they're natural superclasses. So for instance, I can, instead of classifying among the animals, I could group like, whales and dolphins into aquatic mammals, and cars and trucks into vehicles. And so I can do natural versus not natural and get two-way classification. I can do these CFAR 20 superclasses. And so I can, without changing the underlying input data, I can change what the set of target tasks are. And that's what this plot on the left is the color is now colored by the number of target classes. And we see that has a relatively weak effect on the scaling with data set size. In contrast, if I change the input data, say by corrupting CFAR CFAR 10, I see a more dramatic change on the exponent. So this sort of maybe paints a picture where what the model is doing is it's learning some representation of the input data, and then sort of the class labels or perhaps decoration on top of this. All right, so now I kind of want to, in the last few minutes, I'm gonna sort of shift gears entirely and talk about, I started this talk by showing like, look, if you just scale up, you can do better on some tasks, and you can, your performance can improve. And then the rest of the talk was sort of coming up with some picture and models where you could understand this explicitly. But then there's sort of a question of like, okay, so what? So does that mean all I do, is scale up and stop thinking? What's the direction I should take given the fact that performance improves with scale? And I think this perspective, at least for me, helps sort of shape what are like interesting research directions, interesting questions to think about, and what aren't, or at least how to think about questions. So, you can ask for a given problem that, you think is an important problem to solve in machine learning, like, is it practically solved by just scaling up, or is scaling up is it not improving with scale, or is improving with scale so slowly that I need some new ideas to actually solve it? And so here's some work in progress sort of along this direction. So here what I'm showing quickly is some work looking at this problem of catastrophic forgetting as a function of scale. So just to remind you, the catastrophic forgetting setup is you have a sequence of tasks that you'd like to train a single model on, and the hope would be that you could just keep training your model and it would learn to do new tasks. But in practice, what you typically see is that if you train on task A, so here I'm showing task A as a 5-way classification task on CFAR. If I train on task A and then train later on task B, typically my task A performance degrades. And the plot on the right is taking large pre-trained ResNets, let's say smaller to large. So these are pre-trained, not on CFAR, but on ImageNet 21K. And we're plotting on the x-axis is the accuracy on the first task, and the y-axis is the accuracy on the second task after fine-tuning first on task A and then on task B. And the different points represent different learning rates or time steps throughout this fine-tuning process. And we see that the models tend to trace out some Pareto frontier. So for instance, if you didn't train very long, or you had a tiny learning rate, you would continue to do well on task A. And if you waited a long time, you would do well on task B, but you would do worse on task A. But the point is that as we scale up the underlying models, this problem of forgetting gets less and less problematic. So we can, the optimal point, say, of this Pareto frontier just moves out towards doing better on both task A and task B. And just to drive this home a little bit more, here's taking a similar pre-trained model, this time a vision transformer, and here we're training it on 10 class splits of CFAR 100. And so we take our model, if we look at the dark blue curve, this is the performance on the first 10-way split, and now we train it on 9 more 10-way splits, and the performance doesn't really degrade even when trained on these 10 subsequent tasks. Okay, so this type of question, like, does difficult thing in machine learning get solved by scale? It would be nice to try to ask this for a whole range of tasks and sort of get a picture of like what, qualitatively, like what are the things that are hard that are not solved, and what are the things that maybe just scaling up is enough. And so to try to do this, I'm going to give a plug for this benchmark that we're trying to put together, which is called Big Bench. And the goal here is like it's an open appeal to the entire academic community to submit tasks, in this case for large language models, that you think might be hard or particularly interesting to probe how performance changes with scale. Google. Google has agreed to test these tasks on our models. OpenAI will test it on the GPT style models. It's an open benchmark, so anyone can use it on their own models. The hope is to understand, what kind of tasks improve, what kind of tasks don't, and use that to inform future research. Just to give you some examples, like, on the left is a translation task where we see, systematic improvement as we scale up the number of parameters. On the right is a task where you're given pairs of inputs and you're asked to say which caused which, and we see that the model doesn't seem to be learning that with scale. One word of caution is it can kind of be tricky to detect wrong answers. So for instance, there's a task which is asking simple knowledge questions. So for instance, the question is like, what's the human organ that pumps blood? And you see the model outputs like a clearly wrong answer, which just looks like garbage, BXF0, X9F. But then if you go and you say like, oh, well, what is that if I actually like look at it? It turns out that's the beating heart emoji. So like this is an example that we scored as wrong, but then it turned out the model, was a little smarter than us. There's a bunch of these fun wrong examples. So like you can ask the model to repeat the word dog 4 times, and it says the word dog, the word dog, the word dog, you ask it word problems, like there's an empty fruit basket, then one fig is added, then one plum is added, then one date is added, then one plum is removed, then one fig is removed, then which fruits are in the basket. But these models were trained by scraping the internet, so it thinks the most natural response is that this question would get 71 views, and a question that might get more views would be 2 boys can finish a piece of work in 12 days, while 3 boys can finish it in 8 days. How long will it take 1 boy to finish? And that would get over 1,000 views. So maybe you should ask that instead. When asked to translate phrases to Pig Latin, the model often just responds "Ukfe ofye." Anyways, so these kind of things can make it hard to actually understand the wrong answers. But the point is there's this benchmark, and the deadline, the official deadline for submitting, unfortunately, was June 1st, but we have been getting submissions post deadline, and if you had some particular questions that you would like to ask large models or like to see how these things scale across models, I would definitely encourage you to submit. And also the hope is that this will be like a living benchmark, so there'll be future versions if you want to submit. Physics questions are welcome, and so please, if you have any questions, reach out or just submit your task via GitHub pull request. They can be submitted just as simple JSON question answers, or if you want something complicated, it can be arbitrary Pythonic tasks. Okay, so yeah, I think with that plug out of the way, I think that's all I wanted to tell. Thank you.
Thank you, Ethan. I guess we have a little bit of time for questions still, if anybody has some.
So you mentioned that the kernel spectrum follows power law decay, and you implied that this is a well-known fact, or it follows from some well-known facts. Can you talk more about this?
Right. So the well-known is these bounds on. So if you have like bounded operators on d-dimensional manifolds, then there's classic mathematical results about their spectrum. So like one way to get some intuition for this is that if you for instance consider a trace of an operator or the trace of the nth derivative of an operator, and you write this in terms of like if you write this operator in terms of some decomposition in terms of a complete set of functions on that space times the spectrum, if you want this trace to be finite or the derivatives trace to be finite, then you had better have that the spectrum decays sufficiently quickly. So it's that kind of argument that leads to these, if it's smooth then and bounded, then you have this bound on the growth or minimal decay of the spectrum. Does that make sense?
Yes, it makes sense. I'm just wondering why MNIST itself would show this power law decay. So
yeah. So I mean, right. So the like intuition, but of course this is like a far cry from like a precise result, is something like you have this bound, you have an operator which has to satisfy it. That doesn't mean that it saturates it, but then the thought is that just that there's some universality going on here where generic smooth operators saturate this bound rather than like this isn't random matrix theory universality, but it's the same style where generic spectra look this way. But yeah, I guess I think there's a bunch of questions there, like for instance, like how did you know what the D was going to be for MNIST? Like, is the statement that it should be generic on some smooth manifold? I'd say there's a lot there that I don't, understand well.
Maybe I can ask a related question, which is that you referred to the while law when you sort of made this comment. And I think of, or at least the version of the while law that I'm familiar with is a statement about the spectrum of a Laplacian on some manifold. Is the intuition here that like, any sufficiently random looking operator is like the Laplacian on some manifold? Is that or is there some more precise statement version of the while law that applies to generic operators? Or is it just the intuition that you stated earlier?
So, I mean, I think that, that intuition is probably right, but yes, there's a more precise, more general statement about smooth operators that like one can derive this without saying, oh, it's because it's probably the Laplacian. I think that intuition is correct, but you don't need to use this in the derivation. One way to derive this is I mean, there are a few ways to derive it. So like one way to derive it is like if I have a particular manifold in mind, like let's say like a D torus, then I can use this like basis of functions argument that I just described as a way of deriving it. That doesn't like rely on it being the Laplacian. It just relies on it having a decomposition in terms of complete set on this space, and that's fine. Another sort of, you might be like, okay, well, I don't care about D toruses. How do I derive this more generally? Then there's more you can say. One thing is that here I'm probing the short distance structure of the manifold when looking at the asymptotics of this spectrum. So again, then it doesn't really matter that it's a D torus.
You're saying as long as it's smooth, it's completely universal.
Yeah, so that's one way to say it. You can also then say like, well, that's again too hand wavy. I'd like to just stop blabbing and actually derive it. And so I mean, one way you can do it is you can look at piecewise constant functions on an arbitrary manifold, and then you can bound the spectrum for piecewise constant functions, and then look at how that scales as the number of pieces grows. Is another route to proving these kind of statements.
Maybe I can follow up on that. So like, if it is true that if you took your favorite data set, like MNIST, for example, there's some intrinsic parameter associated to that, which is the dimensionality of this underlying space, what would be really interesting is if there was more than one thing that was determined by that parameter, so that you would then argue, like, so far you've argued that in this resolution limited case, the loss scales as a power that's determined by this parameter. Are there other quantities of interest? Like, could you use this to make a prediction that if you could determine one scaling, you would get another law for free? Like, can you like power laws like this are most interesting if the exponents describe more than one thing, right?
So yeah, I mean, so totally. So here's one example.
I guess you had the different classifications in CFAR where you had divided, into different categories, and you found the same coefficient in each. I guess that would be an example of that. Was that what you were thinking about?
Well, here's another example. I mean, you might not be happy with this, but in the kernel case, you have this spectra of the kernel, which then like predicts the scale. Like, so there's a scaling of that, and then there's that then gives you the scaling with respect to data set size and parameter count. And so you can, so that gives you, I mean, there you have these three. I mean, you might not be excited because you can derive that they're related, but you didn't know this a priori. So you have now a relation between the scaling of the loss if you change data set size, the scaling of a loss in a like very different model, right? But now with model size and the scaling of the spectrum. So you have this like duality between data set size and model size scaling. So that's shown here as like this dashed line would be if the model size and data set size scaling were the same, which is what the asymptotic theory gives you, and the solid dots are empirical measurements of that. And these open circles are like, okay, well, how about the kernel spectrum? And so, the prediction is that all of these scalings are the same, but that's, in one case, you have some small number of features, you have a large data set size. In the other case, you have totally different features, large number of features, and you're changing data set size. So they're not like obviously the same thing. And the prediction is that they should asymptotically scale the same. And in fact, the prediction goes beyond that, even outside the asymptotic regime. So we have some plots showing like the loss as a function of data set and model size, even for when you're not in this power law regime matching. Then there's another piece, which is like, let's say going to more general case than these linear cases, which is there's like the loss scaling, but then there's also the nearest neighbor distribution scaling. And so that's, again, I mean, maybe you don't like it because it's like one could be upset that it's sort of they're too closely related, but they're not exactly the same. And so there's a prediction that actually is not perfect, and we'd like to understand better. So here's an example of this, which is like if I look at, so I could look at the data set size scaling, or I could look at the intrinsic dimension measured from nearest neighbor distances. And so for teacher-student models, for instance, but now deep teacher-student models, not linear models, this prediction of like 4 over alpha D for ReLU networks seems reasonably good, but we have these outliers that we see for CFAR data sets where they look more like this sort of more general 2 over alpha D. And I think we'd like to understand that discrepancy better. But that's just to show you that these things don't have to match.
Thank you.
Yeah. I mean, also, I would love to have a constructive way of getting like what, like here I just measure, like there's no theory of like how to actually understand that dimension other than measure it. Sorry.
Yeah, my question is also on measuring that intrinsic dimension of the data. Is there like, one can obviously go in the way of like compressing the images down in the sense of like looking at smaller input sizes, but one could also think about the other way of embedding it into a larger space. Mm-hmm. Does the scaling change? Does this intrinsic dimension remain the same?
Yeah. So I'll answer the question. Let me just say a clarifying point, which I think might have gotten lost, which is here what I'm really describing is not necessarily the intrinsic dimension of the data itself, the input data, but it's of model features evaluated on the input data. So the model is taking that data, compressing it to some like representation data manifold. And so that's just to say it's not like we have necessarily some universal answer for this is the dimension for MNIST or for ImageNet. It really is a combination of like, it has to do with how the model is representing the data. So just want to make sure that's not lost. But yeah. So, but now let's say so I think given that, I could ask your question in a few different ways. One is like if I add irrelevant directions to the input data, but then put it through the same model so that my representations that I'm looking at are still the same dimension. Or I could say, take those representations, add a bunch of like noisy directions to those and say, can I recover the intrinsic dimension? And so again, this is just, so theoretically, if I measure nearest neighbor distances in this case, and in the asymptotic limit, these irrelevant directions should not matter. Let's say added to the feature, added to the features. So like if I just, but then you can ask, but like, is that true? I actually want to measure that in some situation that I care about. And then the answer is it can matter to some degree. And like these measurements at the moment are not super precise. So like we have done experiments where like you take data on a cube, then you push it through like a random network, then you add irrelevant directions, and then you just use your nearest neighbor algorithms to reconstruct the dimension. Like how well does it work? And the answer is like, well, it works okay. And if I add more directions, I start to do worse and worse. And like, it's like relatively stable, but I can easily get variations on 10%. And if I increase the number of dimensions a lot, then I can just totally ruin this measurement. So it's definitely, not perfect, and in practice sensitive for a finite number of points that you're using, sensitive to those kind of things.
Okay. No, but that's already a cool impression, yeah, to see that. Yeah, it's at least a little bit stable, like in some, at least a subset of, subset of experiments.
One thing I'm wondering, does your analysis suggest that it's better to use deeper networks, or is that kind of fall outside?
Yeah, that's a good question. I think that's like, from what I said, that is not, I don't think I have a backup slide on this. You can't get any insight from that, I don't think, from what I told you. We have some plots in the paper where, in the limited context of like wide ResNet on CFAR type data, we look at varying width versus varying depth. And like, do changing these factors change the exponent in terms of data set size scaling? So like a clear signal that depth would be better is like somehow if you vary depth, you saw that your effective dimension was much better. These are like, I'd say like not, I would take these experiments with a grain of salt. What they seem to depth was, so width changed a lot in that if you made the width too small, you could make the exponent worse. But once you got big enough, you never did better with width. So you sort of saturate, once you had enough capacity, you sort of saturated at some critical scaling, and depth, you sort of maybe saw a similar thing. And so like in the regime we were looking at, I think like more depth was more helpful, but then it still was like, once you went big enough, then you sort of but again, take with a grain of salt. It seemed like you reached some capacity, some limiting scaling with respect to data set size, where adding more depth and adding more width then stopped helping.
I see. I guess I'm wondering about the math. So you're looking at the infinite width limit, and I'm wondering from the math, can you do better than linear models? Because, yeah, so is there any suggestion that going beyond linear models is better?
Is better for performance, or like you can, is that what you're asking?
Right. So I'm just, because when you're looking at infinite width, kind of like a linear model, deeper networks sort of look like linear models already. So I'm just wondering if there's anything that's suggesting that's specifically for nonlinear models in the analysis, or is the analysis the same for linear and nonlinear?
Let me make sure I understand the question. So there's like the model size scaling that's variance limited, where you scale width, and you can ask, like, in that case, am I doing better as I make my model, for nonlinear models, am I doing better as I make my model wider? There's also like the data set size scaling in that same regime, and you can ask, if I make my model wider, is my data set size scaling better? Which of those questions was your question? One of those in particular?
Yeah, I guess my question was whether, so this math analysis you talked about, it also applies to linear models, right? Or is it more specific to models which are not linear?
Here by linear, do you mean that the features themselves are linear, or do you mean that the model is linear in some nonlinear feature? Like, so the analysis of the kernels that I described was linear models,
a model, like
features.
a neural network with no hidden layers. You just have like logistic regression.
Mm-hmm.
I guess it was
yes.
Because when you're looking at infinite width limit, models look like they're linear. So I'm just wondering if all of this analysis applies to logistic regression, or is there something that's more specific to something that's beyond logistic regression?
So totally, as models get wider at fixed data set size, they approach linear models, and so all of the analysis that I talked about for the linear setup holds in that limit. Of course, you can't simultaneously be in that limit and think about like large data model size scaling, because that necessarily is the limit where that width reducing you to a linear model breaks down, right? Like, for that to be true, you have to have data much less than model. So the thing, the regime where you can use that perspective that like wide models are linear is the regime where you're over-parameterized, and you can either ask about over-parameterized scaling, in which case you can ask, does going even wider help you? And the answer is yes or no, depending on the setting, but it's always helping you in a kind of a subleading way. And then you can ask, if I go beyond, like, now I can ask about the data set size scaling, and how is going beyond linear in my analysis helping me in terms of that data set size scaling. And again, that's a subleading effect. So I have something like d to the minus alpha as the scaling coming from the linear analysis, and then I would have that suppressed by a 1 over width of the network component in my loss coming from including the nonlinear effects in that analysis. So which is yeah. Subleading,
okay,
but
got it.
Yeah,
makes sense.
Yeah.
All right, thanks.
Okay.
Any other questions? If not, maybe we'll end there. And thank Ethan once again.
Thank you, Ethan.
Thank you guys. Nice chatting.
Actually, I had one